Electricity, Section 4. Let's start with batteries. You'll notice that what you can do with batteries is essentially the same thing you can do with a hydraulic accumulator. You can have power in case of an emergency, and definitely you can use batteries to start engines, which of course we're all practiced with, and smoothing the voltage during load changes. Just the same as, and I'll leave out all the minor details here. If we turn on a lot of components all at the same time, and we have a voltmeter in our system here, if we turn on a whole bunch of components at the same time, it's just like turning on a bunch of water faucets in your house. The pressure tends to go down. Wherever that voltage is, it tends to go down. Now that generator or alternator that we've got, it's going to pump more amps into the system, but the lines of flux in the field have to expand or contract, and that takes time. So the voltage regulator cannot cause the generator to react instantaneously. So it's going to take a half of a second or a second. In the meantime, the voltage might go too low and things might not work. So let's just say the voltage regulator is set somewhere between 27 and 28 volts. So we're sitting here cruising around 27 volts. This voltage, if we watched it very carefully, it would only come down to about 25.2, because in a 28 volt DC system, the battery that we're going to have in here, brand new fully charged at 80 degrees Fahrenheit, is going to be 25.2 volts. So the volts are only going to drop a couple of volts. Also, if amps are coming out of the generator and powering our motor, powering our light bulb, and all of a sudden we turn these things off, the amps have to go somewhere, and guess what? They can go into the battery. If they didn't, the volts, instead of staying at 27, the volts might go up to say 35 volts for just a moment while the voltage regulator makes the generator put out less amps. But during that half of a second or a second, we're pumping too many amps into the system. Just like if you had a house and had all the faucets turned on and a friend at each faucet, and you said mark cassette go, and you turned all the faucets off, the water pressure inside the house would tend to go up. Well, the voltage and the water pressure is very similar. So instead of the voltage going too high, some of those amps could go into the battery. Now you'd overcharge the battery for a half of a second to a second or so, but the battery can handle that. So instead of the voltage going up to 35, it might only go up to 28 or 29. So essentially it's going to prevent the voltage from getting higher than normal or lower than normal. We're not going to go into the theory of operation on the inside of a battery much. As far as we're concerned, we're just pretty happy making an analogy that the positive side of the battery has too many electrons and the negative side of the battery has too many electrons, and they're going to be trying to go around to the positive side. And when they charge or discharge, when the battery charges or discharges, there's a chemical reaction occurring inside of the battery, and so when we discharge it, it occurs in one direction. When we charge it, it occurs in another direction. Batteries only are found in DC systems. When a battery discharges, electrons only leave the negative side of the battery and they try to go to the positive side of the battery. So you're only going to find it in a system where devices work in direct current. So if we've got a 28 volt radio, that'll work out fine. The amps will only go through the radio in one direction. There's no such thing as an AC radio. Okay, amp hour rating. All airplane batteries have amp hour ratings, and that's essentially how much energy will they store. Cars typically, CCA, car batteries tend to rate their batteries in cold cranking amps. How many amps can you get out of it at a certain temperature? But we don't worry about that in airplanes. We're worried about how long will the battery last if something goes wrong. So here, we'll try it. Here's the formula. Amp hours equals amps times hours. I'll give you this formula on the test because you might not be able to remember it. So let's say we have an amp hour rating of 12 amp hours equals how many amps we're drawing out of it times how many hours we're going to drain it. Let's just say, for instance, that we drain, we want it, let's just say we're going to drain 24 amps out of it. 12 amp hours equals 24 times H. So we've got to solve for H. So if we divide by this side by 24, divide by this side, we end up with a half of an hour is how long it'll last if we're draining it at 24 amps and if the battery is rated at 12 amp hours. But I have a rule of thumb here that I think is important. We're going to take how many hours we think the battery will last, and we're going to multiply it by 0.7. Probably sounds familiar. And we're going to say that we're probably only going to get 70% of that original amp hour rating because the battery's probably not fully charged. Essentially, that's what this amp hour rating is based on. It's based on the battery's fully charged. It's based on being at 80 degrees Fahrenheit. And it's based from the moment that it starts discharging. And in real life, the battery might not be fully charged. Oh wait, another one is the battery's new. The battery's brand new. It's probably not going to be at 80 degrees Fahrenheit. We might miss when the battery started discharging. And guess what? It's almost for sure we're not going to have a brand new battery. So we're going to take into account the fact that these things are not all true, and we're going to reduce it by 30% and say, you know what? We're only going to get 30.35 hours out of it. Well, that's just a little over a third. So that's going to be like 21 minutes. That's not very long for a 12 amp hour battery. Okay, well, of course, we could always drain it less than that. Just for fun, let's try another one. Amp hours equals amps times. Well, I think you get the picture. Remember that once you figure out how many hours it's going to take, you're going to take the hours and multiply by 0.7 to give you your actual time before it goes dead. And now we're going to take a look at battery circuit ammeters and versus generator circuit ammeters. Here is an generator circuit ammeter. You notice it's sitting here at 0. They didn't put the numbers very well, but there's 0, and right over here is at 50. And, well, we'll get into these pictures here later. And here's what you're used to if you're flying 172s, negative 30 amps, positive 30 amps, and the amps are telling you if the battery's discharging. So I'm going to do something you normally wouldn't find, and that would be to find an aircraft with an ammeter in series with an ammeter in the battery circuit. So this right here is the battery circuit. Battery circuit ammeter. And here's an ammeter that's in with the generator. I've never seen an airplane that had both. And this would be, say, 0 over here, and we'll just say it's 0 over here, and we'll say that this generator can put out 100 amps. And so, of course, we're going to hook things up into this system, like a light bulb and a motor and all kinds of other stuff. If we turn on the master switch, and okay, forgot this one here. This is the generator circuit ammeter. So now we have both kinds of ammeters. If we turn on the generator circuit, if we turn on the electrical master switch and allow the positive side of the battery to get connected to the bus bar, if the motor, say, in the turn coordinator is working, it's going to drain. If we've got the beacon on or some radios on, it's going to be draining. Now normally, if we haven't turned anything on, the ammeter is going to show 0. But if the battery is draining, the ammeter comes over on the negative side. Once we get the engine started and turn on the generator, then the generator is going to be not only feeding our components, but the generator is going to be charging the battery, so the needle's going to come over to the positive side during charge. So effectively, a battery circuit ammeter tells you if the battery's charging, tells you if the battery's discharging. Of course, it tells you how many amps, and then if it's right smack on zero, it'll tell you that it's not discharging at all. Oop, too much there. Now, let's say we get it, the engine started. Well, the starter motor took a lot of amps out of the battery, took a lot of power. So at first, the needle's going to come way over. But over the course of 5 or 10 minutes, the needle's going to come back down. Typically, if the battery is fully charged, this needle is going to be slightly to the right, and it's going to show 1 or 2 amps. That's because the battery is at 25.2 amps if it's brand new, fully charged, in a 28-volt DC circuit. And the voltage regulator, which I didn't draw in yet, the voltage regulator is going to be making the generator put out amps to keep the voltage somewhere between 27 and 28. So you'll notice that there's a difference of 2 or 3 amps. So the battery is at a little lower voltage, so the generator is always going to be shoving a few amps into the battery, and that energy ends up turning into heat. The battery gets warm, and that's okay, because as it warms up, its resistance gets higher, so it tends to not get charged too much. So you're always going to see the ammeter, if it's a battery circuit ammeter, 1 or 2 amps on the positive side. If we turn on a bunch of things all at once, we'll probably see the needle wiggle, but as long as it stays a little bit over positive, we know that the generator is producing amps to power all of our stuff, and we know that the generator is producing enough amps to charge the battery. So when the engine is running and the generator's on, we can also use this battery circuit ammeter to tell us how well the generator is working effectively. A battery circuit ammeter directly tells us about the battery, and it indirectly tells us about the generator or the alternator. Now let's try the generator circuit ammeter. We go out to the airplane, we turn on the master switch, and that connects the positive side of the battery to the bus bar, but the generator's not spinning, so the needle here stays at 0. Do we know if the battery's getting discharged? Sure we do. We don't know exactly how many amps, but these ammeters aren't that accurate anyway. So we turn coordinator spins, we run some lights, we run some radios. Of course we know the battery is discharging. We get the engine started and turn on the generator, and as soon as we turn the generator on, this needle is going to move up. Now this needle is going to tell us how many amps the generator is using to power all of our devices, and it's going to tell us how many amps it's being used to charge up the battery, because we drained it a bunch during engine start. And let's just say for fun that this comes up to 30 amps, because all of these other electrons have to go through it. Okay, but as the battery charges up, it doesn't need as many amps anymore, so this needle is actually going to come down a little bit lower. We'll just say to 20 amps. And as long as we see that the amperage came down, then we know that the battery got charged. So the generator circuit ammeter, it directly tells us about the generator. Whoops, can't even spell generator. And indirectly tells us about the battery. If we turn more things on, and the generator has to put out more amps, then the needle will come up. Every time we turn something on, if it's a generator circuit ammeter, the needle will go up. Every time we turn something off, the needle will go down. So as long as every time we turn something on, the needle goes up, then we know that the generator is producing enough amps to not only power any extra equipment, but it's also putting out enough power, enough amps to charge the battery. Let's say we turn something on. Let's say that we've turned everything on until the needle comes up to 100 amps. And now we turn one more thing on, and the needle doesn't move. It stays at 100 amps. But if we turn that thing on, it'll still work. The reason why it'll still work is because, and the generator's not putting any more out amps than 100, is that now the battery is providing the amps for the extra component. So we can still indirectly tell if the battery's getting discharged. If this needle has come all the way up to the to the rated power of the generator, or it might be off a little bit. If we turn something on and the needle doesn't go up, then indirectly we can tell that the battery is what is producing the power to operate that other component, and now the battery is discharging. We just don't know how much. There's two main kinds of batteries you're going to find in aircraft that help power the electrical system. The first is lead acid batteries. You've probably seen this picture before. There's just like the ones in your cars. There's typically 6 cells for 12 volts or 12 cells for 24 volts. You don't have to write that down. Some of them are sealed, so unlike this one, you can't add water. Here's another one. This one looks like it's sealed. Red is for positive, black is for negative. You're going to find lead acid batteries on aircraft that have piston engines. And of course, these days you might find a diesel or two, but those are still piston engines. So piston-powered airplanes, piston-powered helicopters, piston-powered gliders, piston-powered blimps are going to have lead-acid batteries. They're a lot cheaper than nickel-cadmium batteries, which we're going to get to. Interestingly enough, you go to Kmart, buy a battery for your car, it's $30 or $40. If you buy a battery for 172, it's $300 or $400. If you bought a NiCad battery for your airplane for a 172, it would be $3,000 or $4,000. So it's not really worth it. We'll get into why NiCad batteries are worth so much more money. You're generally going to have two kinds of systems. You're going to have a 12 or 14 volt system, or you're going to have a 24/28 volt system. And there's no difference between a 12 and a 24 volt, 12 and a 14 volt system. It's just the name. You'll notice if a battery, the alternator generator output in this system is going to be 13.5 to 14 volts. But if you double those numbers, if you multiply those numbers times 2, you get 27 to 28 volts. So that's what the voltage regulator is going to be making the alternator generator keep the voltage at. If we had a brand new fully charged battery at 80 degrees Fahrenheit, in a 12 or 14 volt system, it'd be 12.6 volts. That's where this comes from. And if we multiply 2 times 12.6, we get 25.2 volts. That's where this comes from. And you'll notice that the voltage of the system of the alternator generator is always a little higher than the battery. That way the battery can get charged. Whichever component in the system, whether it's the generator or the battery, is producing the higher voltage, that's the one that's going to be supplying the amps to everything else. So we need the alternator and generator to put out a higher voltage. So not only does it power all of the other components, it also charges the battery. Also, if you have a voltmeter in your system, and we'll say that it's a 12 to 14 volt system, normally when everything's working pretty good, we'll have 13.5 or 14 volts. If we turned off the generator or the generator failed, the voltmeter would come down. Oops, I must be pushing a button. The voltmeter is going to come down to 12.6, and then as it drains, it's slowly going to get lower and lower, and by the time it gets down to 11 volts, it's going to be dead. I'm going to say before it gets dead, it'll hit 11. No, the other way around. It'll be dead by the time it gets to 12. In any case, if you multiply times 2, you get 24 volts. So if you're in an airplane that has a voltmeter and it has a lead-acid battery, once the generator quits, it's going to come down to 12.6, and then it's going to continue. It's going to immediately come down to 12.6, and then it's going to continue going down as the battery drains. And you can watch it and know that if it's sitting here coming towards 11, you're on the verge of the battery going dead. So that's a nice way to know, hey, it's about to go dead. Might not be the best way. Oh, forgot one here. Discharge rates, DFM, draw from memory. So memory, here is the lead acid battery discharge, and here's time, and here's volts. And as you drain it, it gets less. And you'll notice I'm not going all the way to the bottom, because the voltage, by the time it gets down to 11 volts, nothing on the airplane is going to work anymore. So we don't have to, so we're not concerned about this. So make sure on the test you don't draw this all the way down to zero, because the voltage is never going to get perfectly down to zero unless you let it sit around for an awfully long time with something hooked up to it. By that time, we don't worry about it anymore. This voltage right here, this would be about 11. So you don't have to draw that in. So it's going to discharge. One of the reasons I have the chart right here is you'll notice that this line here is pretty straight, and it's pretty steep. And you'll notice that there's a direct correlation. As time moves on, volts go down. So that's a characteristic of lead acid batteries, is that as they discharge, their volts go down, which is why you can look at them and watch the voltage go down, and before you get to 11 or before you get to 22 volts, the battery will be dead. Now, unfortunately, lead acid batteries, the chemical reaction inside of the batteries doesn't happen extremely fast. So if you suck a bunch of amps out of it, you might have to wait a while, a few minutes, before you can get more power out of it. The battery doesn't miraculously recharge itself. For instance, let's say you go out to start a piston-powered airplane or a piston-powered car. Run, 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 run. After a while, run, 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 click, 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 run, run, click, 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 click. And then you let go of the key and you turn it again. Run, 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 click, 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 click. You let go and then you turn the key. Click, 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 click. Okay, so relay in there's moving, but there's not enough amps to push the battery around. So you wait 5 minutes and turn the key. Run, 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 and it'll crank the engine some more. It might not start, but it'll certainly rotate the engine. It's because you gave it time. A lead acid battery needs some more time to get the full amp hour battery out of it. So you can't get all the amp hours out of it if you're discharging it at a high rate. You don't have to write this down, but I'm going to say it's probably going to take you about 20 minutes if you really wanted to get all the amp hours out of a lead acid battery. But that's okay, because lead acid batteries are used on recips, and you only have to crank, what does it take? 2 or 3 seconds most of the time? Maybe even 10 or 20 seconds. You'd still be fine not being able to get all the amp hour rating out of the lead acid battery. And of course, when is it dead? Before it gets to 11. By the time it gets down to 22, it's going to be dead. And we've already covered airworthiness issues of batteries. Lead acid batteries, like in your car or on recips, we're going to say 4. If you completely discharge it, like you leave the lights on overnight, you come back the next day, it's dead, you jump start it, and it'll work and it'll recharge. But every time you have a complete discharge of a lead acid battery, that's bad for that lead acid battery. And after you do it too many times, then you've noticeably reduced its amp hour rating, and you've noticeably reduced the ability to get a high discharge rate out of it. So that's kind of a generic number. It's going to vary by temperature and battery brand and how complete you actually discharged it. But remember that if you've drained your battery 2 or 3 times in your car, one of these days you're going to come out there on a nice cold morning and it won't have enough amp hours in it to start the engine. The voltage won't be high enough to crank the motor. NiCad batteries have nickel and cadmium, just like lead acid batteries have lead and sulfuric acid. Woohoo, sulfuric acid. NiCad batteries have nickel cadmium metal and potassium hydroxide, which instead of being acid is a base, but base is just as bad for you as acid. So if you were ever going to service NiCad batteries or lead acid batteries, which interestingly enough is in FAR 43 Appendix A under preventative maintenance, you would want to wear safety goggles. I hate it when I get acids or base splashed in my eye, and I won't get into that story. Here's a picture of a NiCad battery. Here's another picture of a NiCad battery. A lot of times they're squares or cubes. You're going to find NiCad batteries on turbine-powered airplanes. Now, you notice I say typically. I have seen 1 or 2 recips have a NiCad, and I've seen a very few number of turbine-powered airplanes have lead-acid batteries. But there's some really good reasons why nickel-cadmium, why turbine engines use NiCad batteries. You don't need to memorize these 2 numbers, but interestingly enough, 25.2 is the same number for voltage for NiCads as it is for lead acid batteries. And you're almost never going to see a NiCad battery on an airplane that's got a 12 or 14 volt system. So we're pretty much talking 28 volt DC systems, and of course some people call them 24 volt systems. So yay, we don't have another voltage to memorize. Brand new, fully charged NiCad battery, 25.2 volts DC. Here's a picture of the top of a NiCad battery. You don't have to draw this on the test, but they're all hooked up in series, and each one of these is a cell. We're looking down on it. In reality, this is probably 4 or 5 times longer than its width. NiCad batteries drain a whole lot differently. Here's a picture I found on the internet. And you notice that as the battery drains, it's relatively flat right here. It comes down a little bit, and then there's a sharp turn. But what I want you to draw is this. Here's what I want you to draw. Whoops. I want you to draw a NiCad battery discharge. We're still going to have time, and we're still going to have volts, just like we did on a lead acid. But what I want you to do is draw essentially a perfect rectangle. In fact, I want this corner right here to be sharp. Now that's not exactly, you'll notice, that's not exactly like this right here. It drops a little right here, and we have a curve right here. But I want you to remember this this characteristic of a NiCad battery is that as the battery is discharging, okay, so this is a NiCad discharge. So as this NiCad battery is discharging, you'll notice that over time the voltage doesn't change. We're going to say it doesn't change much at all, and we're going to say all of a sudden, whoosh, the voltage is going to drop, and you're not going to get anything out of that battery. So my concern is that people would be right here thinking, oh, look, I got 25 volts, or I got 24.8, it hasn't changed very much, and I got plenty of time. Well, guess what? It might only be another 30 seconds where the voltage drops like crazy, and if the voltage gets down, we probably don't remember E over IR. But if voltage is not constant, if voltage goes down, resistance is constant, amperage is going to drop. So if we have low voltage and we have low amperage, then we're not going to have very many watts. You probably don't remember, but power equals amps times volts. So if both of these numbers are getting less, then watts or power is going to go way down as well. So, of course, draw from memory. Amps and volts during rapid discharge. This is one of those great things about NiCad batteries, is that the amps and the volts can stay relatively constant. They're not perfect, but we can drain it really, really fast, and the voltage and the amps don't go down. You got to remember, here's the lead acid battery. Volts go down. If we use that formula again, P equals I times E, and E over IR. If volts go down and the resistance is constant, amps will go down. Okay, so amps here is going to go down. Oh wait, volts is already going down. If both of these go down, watts or power available is going to go down like crazy. So if we're talking about how much power is available to a starter motor in a lead acid battery, then we're going to drain that battery. Available power coming out of it is going to drop really, really fast. If it's a NiCad battery, where the voltage stays relatively constant, if volts stay up, if resistance doesn't change, then current flow will stay relatively high. If current and volts both stay pretty constant, then power to the starter motor stays pretty constant. The reason this is a big deal is if you take, and this is why you're going to find them on turbine-powered airplanes. Here's our turbine-powered airplane. Air comes in, air goes out, and we're going to have an accessory section with a starter on it. So the starter motor is going to add energy during the engine start to spin the shaft around. The reason why we want to spin the shaft around is because we need cold air to get blown into the engine by the compressor. The compressor is just a bunch of fans, two S's, and it's going to blow cold air into the engine. As soon as we turn on the fuel and squirt fuel in here and catch it on fire, the temperature is going to go up dramatically. The only way you can cool a jet engine during start is to spin this compressor around and get cold air to come through the engine. And guess what the starter is doing? The starter is spinning the compressor. So if the starter reduces its power, then the compressor will slow down, will be burning this fuel, and the temperature will get too high, and we could have what's called a hot start. And this is a really, really big deal on jet engines. is to not have hot starts. That's why it's very expensive, but it's worth it, because NiCad batteries will maintain their amps and volts relatively constant during an engine start when we're draining it very rapidly, and that'll allow the power to stay really, really high. The compressor will spin fast, and we'll get nice a lot of cooling air through the engine, and it will prevent a jet engine hot start. And of course, we can get the amp hour rating out of it. If there's our drain, when this voltage drops, this area in here is effectively its amp hour rating. We can suck all that out. When I say high discharge rate, I'm talking about 2, 3, 4 minutes. We can get every amp hour out of it. So, here's a big issue though. When is it dead? Well, if we look at that discharge graph, and we're right at this point right here, here's time, and here's volts. We don't know when it's about to go dead. Maybe we should say when is it about to go dead? And the question is, we can't tell, we cannot tell by checking the volts. No way, we can't use the volts. We're going to have to use the amp hour rating. We're going to have to use the amp hour rating to know when it's about to go dead. Thermal runaway. Lead acid batteries, like most other conductors, when you get them hot, their resistance goes up. So thermal runaway doesn't apply to them. Thermal runaway only applies to NiCads. They're opposite to most conductors. In what way? Is that as the temperature goes up, the internal resistance goes down. So that gets kind of funky. What that means is that if a NiCad battery gets too hot, its resistance will go down, and now you'll be able to overcharge it. And overcharging the battery is not going to be a good idea. So what are the things that can make NiCads get hot? Well, whenever you charge it, you're pumping amps through it, and whenever amps go through a conductor, it's going to get hot. Well, if the amps go in the opposite direction during discharge, amps going through it in the opposite direction, that's going to cause it to get hot as well. Of course, we could have environmental factors. We could have a hot day and a hot ramp, and those could make it hot. Worst case scenario. Well, we don't have to get into worst case scenario, but those are the things that make it hot. So, the most likely time to occur, here, I'll give you that scenario. Let's say you land the airplane at Death Valley, California, in the middle of the summer. You land it there at 9 in the morning. You come back at 4 o'clock in the afternoon. The air temperature is really hot, so the inside of the battery compartment is hot. The ramp gets black asphalt, gets hot. It's going to heat up the inside of the airplane because the hot air is going to rise up and heat the airplane up. So we go out to the airplane. Let's just say it's a twin engine airplane like a Beech 1900. It's got jet engine, so it's going to have NiCad batteries on it. So we go to start one engine and we discharge it like crazy, and the engine doesn't start. So we let off the starter. We figure out, we forgot to turn on a fuel valve. So now we discharge it again, some more, to get the first engine started. Well, as soon as we get the first engine started, we're going to turn the generator on, and so it'll start charging it, but we're immediately going to start up the second engine, and the first generator won't put out enough power to start the second engine, so we're going to discharge it a little bit more. Then the second generator will get turned on, and then we're definitely going to charge it up a lot. Well, we had a hot day. It was already hot. A hot ramp made it hotter. We discharged it 2.5 times, and now we're charging it like crazy. So guess what's happening to it? All of these things are making the battery hot. Problem is, as the temperature goes up in a NiCad battery, unlike a lead acid battery, that's going to cause the internal resistance to go down. So if we have a constant voltage system, because we have a voltage regulator, so let's just say, here we go. Here's our battery. And of course, we'll just make it simple. We'll say one generator. But we got that voltage regulator on it, and it's set to maintain the voltage at 27 to 28 volts. And so the generator is going to be pumping amps into the battery And if its resistance gets less, remember E over IR. Probably never heard of that before. If the voltage is constant and the resistance gets less, that means the current flow is going to go higher. So as we're charging the battery and it gets even hotter, the resistance gets less and we can charge it up even more. Except the electrons going through the battery, that's going to make it hotter. If it gets hotter, its resistance will go down and its amperage will go up. If its amperage goes up, it'll get hotter and its resistance will go down. So its amperage will go up, all based on having a constant voltage system, and that's what we do in airplanes. We have constant voltage systems. So it's going to run away. The temperature is going to run away, hence the term thermal runaway. It's also called vicious cycle. Let's see. A good definition of thermal runaway would be on a NiCad battery, when the temperature gets high enough, the internal resistance gets low enough that the battery will be dramatically overcharged. Let's see. I'll try that again. In a NiCad battery, if the battery gets hot enough and its internal resistance gets low enough, the battery will get dramatically overcharged, and we'll put another part in there, and damage will occur. And the damage is typically twofold. The heat will tend to make things expand, and the battery will burst. It doesn't explode like dynamite, but it'll burst. And I've actually heard that sound go boom. It sounds like a very small bomb. And the other thing is the heat will cause the wires inside the battery and cause the wires touching the battery to get so hot it'll melt the insulation, and now you could easily have an electrical fire. So batteries bursting and electrical fires are the two negative consequences of having thermal runaway. Here are a couple of cells. Now you can see them, how tall they are. You can see how they've gotten bigger and they've burst and broken. It's not a pretty sight. And here's a picture of a temperature gauge for a battery. You notice it says battery temperature gauge. So the only thing you can do with that battery, if you're flying along, and we've got that generator putting out amps and pumping up the battery, the only thing you can do is to disconnect the battery so that the amps can't go into the battery anymore. The battery will still be hot, but at least it won't get any hotter. At least it won't get any hotter. And of course the battery is going to be unairworthy now. Do not reconnect it to the bus bar unless you think you're going to die, because dying's probably not quite as bad as having the battery burst and having electrical fires. The only way you can prevent it is to have maintenance done on the aircraft as scheduled. Make sure that the scheduled maintenance gets done on the battery on schedule. That's one of the few things I found in pilot operating handbooks and approved flight manuals where they tell the pilots what the maintenance schedule is for something on the aircraft, because it's that important. Also, most likely time to occur, that battery inside of that box, it doesn't heat up. Thermal runaway doesn't take 2 or 3 minutes to occur. We're going to say it takes about 20 minutes once it gets rolling to actually get to the point where the battery's going to burst or we're going to have an electrical fire. So if you're in that twin-engine turbine-powered airplane at Death Valley and you start a thermal runaway when you get the second engine started, where are you going to be 20 minutes later? You're going to be in a climb. You're going to have already taken off, and you're going to be in a climb. So what I recommend, now it's not that thermal runaways can't occur during other times. That is absolutely true. But if there was one time you had to pick and say, when was it most likely to occur, you'd say shortly after takeoff. So what I encourage you to do is put that battery temperature gauge into your scan during climb at a greater frequency than you would a lot of other times. There's actually an airworthiness directive out that says any aircraft, it doesn't apply to specific makes and models of aircraft, it says any aircraft that has a nickel cadmium battery in it has to have some type of temperature warning system for the pilot. So since this is required by AD, you couldn't use this under the 4+3 method in Part 91, because an AD is requiring this battery gauge, temperature gauge, to be there. And I bet you the FAA wouldn't approve your minimum equipment list to go flying without your battery temperature gauge. But when that AD came out, they started putting temperature gauges in airplanes that had NiCad batteries, and they put them in some obscure place. So, for instance, if here's the instrument panel, and let's say it's single pilot IFR, and you're sitting over here, and they put the battery temperature gauge way on the other side of the instrument panel, you're really going to have to look for it. So when you're going to look for it more than usual, you're going to look for it in a climb. Prevention, I already told you that part. Get the battery maintenance done on time. If you've ever operated a NiCad battery in a cell phone or a remote control vehicle, you've heard of a thing called battery memory. You drain it halfway, charge it, drain it halfway, charge it, drain it halfway, charge it. And then you can only get half the amps hour out of it. How do you get rid of that battery memory? By draining it completely dead and recharging it. That's one of the parts of this scheduled maintenance. It's called a deep cycle. You drain it till it's completely dead and then charge it back up again. And draining it completely dead is actually good for NiCad batteries, so it's an infinite number. There's no restriction on how many times you can completely drain a NiCad battery, because it's actually good for it. And here's the possible gauges you might need to monitor in a DC system. Obviously, we've talked about the voltmeter, low voltage and over voltage lights, and the ammeter, either battery circuit ammeter or generator circuit ammeter. Now we're going to add another one there, the NiCad battery temperature gauge. And of course, if the battery goes dead, you're going to want to look at your watch or your clock to time how long it's going to take for you to wait for the battery to go dead. So in that case, you would need to know the amp hour rating of the battery. You'd need to know how many amps are being drained, and that would give you the time. And of course, you multiply that by 0.7 to give you the actual amount of time that you would have for the battery to last. If you have any questions or improvements about this lecture, please let me know. And if you feel like it, you can do the connections exercise as assigned. Thank you.